Hello everyone. So welcome to the 10th week of the tutorial session on control systems. My name is Soumya and I am a PMRF fellow at IIT Gandhinagar and I am your TA for the course. So last week, if you remember, we had covered many questions on Bode plots. Today we'll have a few more questions on Bode plots, and once we are done with it, we are going to move to Nyquist plot. If I hope you have already gone through the lectures that are uh, covered for this week, and in the next week we have Nyquist stability criteria coming up. But here now we are going to just focus more on Bode plots, right? And Nyquist plot for this time. So, just I would just give a brief of what we had done in the last lecture so that I can proceed forward. Else, if the terms like 20 dB per decade and minus 20 dB per decade or 6 dB per octave are confusing, then that's a problem. So, I'll switch back to the last slide. Okay, and here what we had basically done, it was a brief introduction to Bode plot at first, where we usually know that we have two plots, magnitude plot and phase plot, right? And the magnitude plot is the magnitude versus omega. So we want to visualize how the plant transfer function varies as omega is varied, right? And the the variation can be seen in terms of magnitude and phase both. So we usually have two, we always have two plots. One of them is magnitude versus frequency, one of them is phase versus frequency, right? Nyquist plot that we are going to see today is basically plotted in PS plane, which means it is the x-axis is the real axis of the plant transfer function, and y-axis is the imaginary axis, right? Now for Bode plot we had seen, I won't go into detail as we had done last time, but there are a few advantages why we go for Bode plot and why do we have logarithmic scale on the x-axis for frequency. And the reasons are the following: that we can cover larger range of omega, right? Because if you go with a linear scale, you can go from like 1 2 3 400 if you go at a span of 1, right? But let's say if you are to measure 0.0001, you won't be able to show that, uh, right? So we want, if you want to show a large range of frequency, definitely it does not have to be uh, arithmetic mean, it has to be geometric mean, right? So that is why in this case, any number that you find out on the x-axis is basically geometric mean of the numbers. So if I say this is A, this is B, and this is C, then A is the geometric mean of B and C. Okay, so in this way we get to have larger range of omega. You see, we started with 0.01, but we could go to 10 to the power 4. The other reason is low frequency region can be expanded. So if you go below this, it is 0.001, right? So we are able to expand this region, which would have not been possible in a linear scale. So those are the reasons why we go for logarithmic scale, right? And uh, the other thing is, the magnitude is represented in dB, and the way to do it is whatever magnitude you get by substituting j omega and finding out the magnitude, you just have to take a log for that transfer function and multiply it by 20. So it should be on a scale of 10, like log 10. So that gives you in dB the magnitude value in dB, and phase remains as it is. Okay, so the basic building blocks for any transfer function are the following, where first is the constant term, second is the integral term, the third one is the derivative, the fourth one is basically a representation of um, what do we call the same integral term, but it is in the form of 1 upon ts plus 1. That means that it has a corner frequency also. So 1 by t is the corner frequency, and based on that we have either low frequency region or high frequency region. So if you look at my previous lectures, you'll be very clear with what is the corner frequency and why do we do this. In the ts plus 1, it is very similar to s. very similar to the derivative term, right? If you remember the Bode plot for the simple derivative term, s goes straight like this at plus 20 dB per decade, whereas if we look at ts plus 1, it is also going up, but it goes up like it moves, it has a slope of plus 20 decade after you strike the corner frequency, right? So this is what something we saw. And if you cannot break your building your transfer function into factors, then you might encounter these forms, and for these we have already seen that the corner frequency is omega n, and we see a minus 40 dB per decade, right? All of the derivations and explanations are already covered in the lecture, so I'll brief you on all of them unless you have some problem. Okay. So for the constant term that we have for Planck transfer function, you can see that it is going to be a straight line because it is just 20 log 10k. So it's a constant term throughout for all range of omega. So it's going to be a constant line, right? If we go for phase, then also there would be phase based on what is the sign of k. If k is greater than 0, then the phase is going to be positive and 0, and if the sign is for k is negative, definitely will have minus 180 degree, right? Here comes the concept of decade. What is decade? When you go from omega to 10 omega, it is one decade. Decade means in orders of 10. So omega, say 10 omega gaye, it is one decade. Similarly, if we go from 0.1 omega to omega, it's again a decade. And if we go from 0.01 omega to 0.1 omega, it is also a decade. Now, if the range is given in this form, that means that this region is one decade below omega, right? And here what do we say? This region is one decade above omega. Similarly, we have the concept of octave. In that case, just the differences, it's in between omega and 2 omega, 0.5 omega and omega. So it's 2 omega and 4 omega, 4 omega and 8 omega, so in multiples of 2, right? For decade it has to be multiple of 10. So we saw with the integral term, and we saw the transfer function, the Bode plot for the integral term is sloping downwards at minus 20 dB per decade. How did we arrive with this figure minus 20? The whole logic is we check for omega. What do we get? We get uh, where have I written it? Yeah, if we check for omega, it's going to be this quantity, right? Minus 20 log 10 omega dB, right? Because why this minus sign is coming over here? Because it would have actually been 20 log 10 gj omega, and if you substitute 1 upon j omega, and definitely we have to take the magnitude, right? So it is 1 upon omega. When you substitute 1 upon omega here, what happens? Because of this inverse sign, we get a minus coming out, and we can have omega in the numerator. That is simple rule of logarithms, right? So this is what we get. Now, so this is at omega. But if you check at 10 omega, what do you get? We get minus 20 log 10 omega, right? And when you just simplify it, you will see it's minus 20 minus the same thing that we had for omega. That means this minus 20 is an extra term that came when we moved from omega to 10 omega. Right. So we have a decay of minus 20 dB in one decade. Now to generalize this, you can check in between 10 omega and 100 omega. You'll see there is another minus 20 dB per decade decay. Right. So that's how we say. So it's a very simple logic that if you, so here what happens, you have a pole coming in, so it would give you an intuition. If there is a pole coming in my transfer function, I'll drop minus 20 dB per decade there. That's the whole. If there is a 0 coming in, so we would proceed with gs is equal to s type of equation, and it would give me a rise of plus 20 dB per decade. That is the easiest way to think. Okay, I'll come back to this point once again. Just let me finish two other. So 1 upon Ts plus 1. So in this case, we have something called corner frequency, right? And based on this and this corner frequency is only to get the low frequency region and high frequency region, and this is just for approximation purpose, because the real Bode plot, if you look, right, if you plot it in MATLAB, what you'll see, if there is a Bode plot, it is not going to have any sharp corner. It would move like this. This corner won't be sharp. But when we draw, what do? We plot it in this way, this and this. So basically we try to get the asymptotes along which the Bode plot is moving. So our Bode plot has sharp turns, whereas in reality it is not. So when we do this approximation, this is really, it is an approximation. It's not the real, but you get to know the nature of the plot, right? So when you look at 1 upon Ts plus 1 and you try to find out what is the magnitude and what is the phase, so you can see we can relate everything with corner frequency, which is 1 by T, right? And so the low frequency asymptote and the high frequency asymptote intersect at omega is equal to 1 by T. At 1 before 1 by T we have different nature, and after 1 by T we have different nature. So you see, before the corner frequency we have the magnitude to be 0 dB always, as shown here, and just right after the corner frequency we have it decaying. Now so this is at omega. Now you check for 10 omega, you'll see that between both of these you'll see that it is decaying at a frequency of minus 20 dB per decade. So from here this minus 20 figure comes out. So this makes the things very clear, right? If we have a pole coming in, then right after the corner frequency corresponding to that pole, we get a decay of minus 20 dB per decade, right? I hope this makes sense. Uh, if we look at if we look at Ts plus 1, which is very similar to derivative, and for derivative we had this plot coming in, right? Now you can see here, right after the corner frequency, the rise is plus 20 dB per decade. You introduce a 0, you get a corner frequency, and after the corner frequency, the rise is minus 20 dB per decade. If you get another 0 coming in, for example, here it is Ts plus 1, there, so if it is uh, T1s plus 1 and T2s plus 1, then you have two corner frequencies, right? What are they? One of them is 1 upon T1 and 1 upon T2. So when you get a corner frequency of 1 upon T1, you have a 20 degree plus 20 degree per decade increase. So if I plot it, see, this is, for example, this is 1 upon T1 and this is 1 upon T2. Before any corner frequency, you will have 0 dB here, right? Once you encounter this first term, which is a 0 over here, right, the nature would be an increment of plus 20 dB per decade. But after you come here, what would happen at 1 by T2? It was already rising at plus 20 dB per decade, but since we have encountered another 0 coming in, which would give another 20 degree per decade rise, that means this would proceed at plus 40 dB per decade. Okay, so drawing the Bode plot is always good. You have to figure out the corner frequencies, and then you have to decide what is the rate at which the things are decaying or rising. But every time you can go with this approach where you see omega, what is the magnitude, 10 omega, what is the magnitude, 100 omega, what is the magnitude. But there is a limit, like instead of testing all of this, it becomes very evident from here that if you have more and more zeros coming in after each corner frequency, you get a rise of plus 20 dB per decade each time, right? If you have a pole coming in, so after each corner frequency you will observe a minus 20 dB per decade decay. Alright, so that is one of the very it's not a ninja technique, but it is one of the conceptual things that you can observe from here, and you can be very fast at drawing the Bode plots. Okay. So I won't go into details of phase plot. Phase plot is as it is. You see at a lower frequency, a corner frequency, and higher frequency, and you get the phase plots as well. Okay. So we had done a couple of questions. I won't go into the questions now. Now let's move to our today's topic. So as I already mentioned, we have a few questions on Bode plot today, and then we'll move to Nyquist plot. The details of Nyquist plot I'll give at some later point of time today during the lecture. But let's proceed with the questions that we have for Bode plot right now. Okay. So the question is, consider a negative feedback closed loop system. Just okay. Okay. Consider a negative feedback closed loop system whose open loop transfer function is given by s plus 1 upon s square plus 7s plus 10. If you factor it, it would be s plus 1 upon s plus 2 upon s plus 5. Okay. Now, the slope in dp per decade of the high frequency asymptote in the magnitude plot of the corresponding sinusoidal transfer function is what? Okay. So, we want to know high frequency asymptote. High frequency asymptote means, so what is definitely it does not have one corner frequency, since it has multiple poles and 0 as well. That means it has multiple corner frequencies. Now, based on those corner frequencies, we have to decide about high frequency asymptote. So I'll go shortly into the details. So how many poles are there? We have two poles, right? One of them is at minus 5 and one of them is at minus 2. How many zeros are there? 0 is just 1 and it is at minus 1, right? So, so what are the corner frequencies? Corner frequency, how you can always find? You have to always compare these two ts plus 1, and every time your corner frequency would be 1 upon t. Okay. So it has to be always represented in this form. So it would be in this way, it would be s plus 1 upon 2 s plus 1, and 2 would come out to be common, and here 5 would be common, and it would be s upon 5 plus 1. So your corner frequency would be 2, 5 and 1, right? So your corner frequencies are 1, 2 and 5. Now let's write here. So let's say we have corner frequency of 1 over here, okay, 2 over here, and let's say 5 over here. Okay. So this is your omega and this is your magnitude of gj omega. Now what would happen when you, let's say our starting point is 0 dB, or we can calculate what is the starting point. Substitute the value of s to be j omega, and then put omega to be 0 in the magnitude, and from there you'll get what is the initial magnitude. So let's do that first. Magnitude is 20 log 10 into j omega plus 1 upon j omega plus 5 into j omega plus 2. Omega tends to 0, that is what we want to know, right? So it's going to be 20 log 10. When you put the value of magnitude in the numerator, you'll have 1 upon omega square, right? Here you'll have 1 upon, sorry, 25 plus omega square. Here you will have 4 plus omega square, and we have to put the value of omega to be 0. So from here you will get 20 log, and here it would be 1 upon 10, right? If you solve it, what will happen? It would be minus 20 log 10. Always the base of log is 10 in this case. So from here it would be minus 20 dB. So the initial starting point is not 0 dB, rather it's minus 20 dB. Okay? Now what would happen? As soon as you encounter the first corner frequency, it's 1, and 1 is associated with a 0. If it is a 0, that means the transfer function is of the form Ts plus 1. So there would be a rise of plus 20 dB per decade. Alright, it would go till 2. Now, at 2, what is happening? 2 is a pole, so this was for 1. For 2, it is a pole, and it is represented by 1 upon Ts plus 1. That means whatever the nature of graph is, it would add minus 20 dB per decade. So it was already going at 20 dB per decade. Now we add minus 20 dB per decade to it. So what is the resultant? The resultant is there would not be any growth, and it would be constant. So the rise here is 0 dB per decade. Okay, and why do we do this? Because this 20 dB per decade that you got after the corner frequency at 2 is still active. It would go on forever, because the corner frequency was encountered here, and after that it has to be always going at plus 20 dB per decade, right? But here in between 2 and 5, it is going to be a constant. Okay, now after 5, what will happen? Can anyone tell me what would happen after 5?
minus 20 decade per month, dB per decade.
Right, right, very good. So it would be minus 20 dB per decade, and the reason is it was already moving at 0 dB per decade, but we encounter a pole, and pole is again of the nature 1 upon Ts plus 1. So the net decay or rise would be 0 dB per decade minus 20 dB per decade. So it was already 0 over here, and we got this minus. So the resultant is this minus only. So we'll see it going this way, and it would go on forever in this way, forever, because we don't have anything coming after it. So this is minus 20 dB per decade. Alright, so the question is asking the slope of the high frequency asymptote in the magnitude plot is what? If it is asking you high frequency, do not consider any other region except the last region. So in the last region we have it decaying at minus 20 dB per decade. So this is the answer. Okay. Okay. Let's move to the next question. If there is any doubt, you can ask. Let's move. Okay. Please explain magnitude calculation. Magnitude, I simply, so we always want to have magnitude in dB. So if you have a transfer function g of j omega, then it's the general magnitude that we always used to find, right? But when we want to go for Bode plot, we want the answer in dB. And for getting the answer in dB, the way is 20 log 10 g of j omega. So just that you have to take log 10. Okay, so that is what we did here. this magnitude, this is a transfer function, we replaced it by j omega and then took the magnitude of that is a simple rule of taking the magnitude in complex function, I'm saying complex number, and it's under root 1 upon omega square. For denominator you have 25 plus omega square ka under root and 4 plus omega square ka under root, and everything has to come inside 20 log 10, right? So from here, when you substitute the value of omega to be 0, in the numerator you will get 1, in the denominator you will get under root 25, and the other term would be under root 4. So it's 5 into 2 basically, so it's 1 upon 10. So that is why here, and after this when you take the log, we already know that if there is a reciprocal, then we can take it as minus, right? So that is why we have got this. Okay, let's move to the next question. Okay, it's the same question. The corner frequencies of the sinusoidal transfer function are, we already calculated it to be 1, 2 and 5. Okay, so I hope there is no confusion here. Okay, this is also something that we already calculated, the magnitude in dB of the sinusoidal transfer function as frequency tends to 0 is what? So we already calculated, right? That is the thing I told you, and it is minus 20 dB is this calculation. I'll put it there also for reference. Okay. So in the fourth question, in the same problem, the phase in degree of the sinusoidal transfer function as frequency tends to infinity is what? So what? Okay. This was our transfer function, and it's asking about as the frequency tends to infinity. So I'll delete the extra part. So here it is. This was our transfer function. So we want the phase for this. What would be the phase? It would be tan inverse omega from the numerator. For denominator we are going to have a minus sign. It's going to be tan inverse omega upon 5 minus tan inverse omega upon 2, right? And we want to find all of this as omega tends to infinity, because we want to, it is given in the question. So it's going to be, from the first term it's going to be 90 degree minus 90 degree minus 90 degree. So ultimately it's minus 90 degree. So this is your answer. Okay, let's move to the next question. In the same problem, the slope in dB per octave of the low frequency asymptote in the magnitude plot is what? So what is the plot for low frequency asymptote? Now, when it is asked for low frequency asymptote, then you have to see the low frequency region only. So if it is high frequency, you have to see the high frequency region, which is after this. For low frequency, we have to see the region before the first corner frequency, and for this region we don't say a name. If it is explicitly asking you in this region, then only you have to reply according to that, else it is just in this region. All right. So for low frequency region, the slope of low frequency asymptote, it is 0 dB per decade, right? This is 0 dB per decade. Okay. I hope there is no confusion. Okay. In the same problem, what is the static position error constant? So I'll just write it once more. GSHS is S plus 1 upon S plus 5 into S plus 2. Okay. So static position error constant KPE is what? Does anyone remember what is static position error constant? No one remembers?
Limit s tends to 0 GSHS.
Yes, right. So it is limit S tends to 0 GSHS. Okay. So from here, what do we get? Limit S tends to 0 S plus 1. Since it is a negative unity feedback, so HS is 1. So it is S plus 5 into S plus 2. Substitute the value to be 0, it's going to come 1 upon 10, which is 0 0.1. So your KPE is 0 0.1. Okay, this is from the earlier lecture itself. I think it was covered in 4th or 5th week of the lecture, where we saw type 0, type 1, type 2 and type 3 system, and then we saw what are the error constants for uh, unit step, unit ramp and parabolic input, step ramp and parabolic input. And then we saw how do we define static position error constant, and then velocity and acceleration error constant, right? All of the, so we had done steady state error analysis for this, right? If you want to revisit those lectures, please do revisit, because you cannot forget these concepts. These are very important and you'll have straight away questions coming from here. So how do we define KP, how do we define KV, how do we define K? All of them are really important, and you have to get well versed with type 0, type 1, type 2 and type 3 systems. Okay, now in the next question, probably this is the last question from the Bode plot. So what is the steady state error? So if you remember, the steady state error is 1 upon 1 plus KPE. So it's gonna be 1 upon 1 plus 0.1. You'll get it equal to around 0.9, right? So your correct answer is 0.9. It should be 0.901 kind of, 909, sorry. So it would be 0.91. All right, I hope this is clear completely. Any questions with Bode plot, because we are going to switch gears to Nyquist plot after this? No more questions? Okay. Okay. So I hope you have already gone through the lecture, but these are just some points that I want to bring forward over here, because this is what Nyquist plot does and what do we infer from there. Okay, so it's definitely a graphical tool. You might have already seen that we plot in the plant transfer function plane, PS plane, and the axes are real part of the transfer function and imaginary part of the transfer function. So our job is always to find the magnitude, to find the phase, and then to always have the real and imaginary part, right? That is what we do, and based on those we can, like, your magnitude gives you where you have to be on the real axis, your phase gives you how you're going to approach the real axis, and then uh, the real part and imaginary part basically tell you where you have to stay on both the axes, right? So we'll see that soon. The magnitude basically gives you what should be the resultant of the real and imaginary part. Okay. So it's a graphical tool used to analyze stability of feedback systems. The stability part we won't see now, that we'll see in the next class. But it's basically how many encircles you make around the -10 point. But that will say that is something related to uh, Nyquist stability criterion. So we'll see that in the next class, but it is a graphical tool that is used to analyze the stability of feedback system, and it is just based on how you draw the Nyquist plot. Once you have the Nyquist plot, you replicate it because it is going to be symmetric about the real axis. Then you have the plot being drawn, then you see how many times it is encircling, and based on that encircling itself you can tell what is the stability of the system. Alright. The second is it maps frequency response onto the complex plane as omega varies from -infinity to infinity. What we typically do is we vary it from 0 to infinity, and we know that it is going to be a mirror image about the real axis, so we get the full Nyquist plot. Okay. The plot is symmetrical about the real axis. It shows how the open loop system encircles the -10 point. Again, this is related to stability criterion, and we'll see that in the next class. Next class is very important once you have covered this topic. And stability of closed loop system is decided using the Nyquist criterion, and it combines both gain and phase information in a single plot. So you see in the Bode plot we had two different plots coming in, and both of them had no relation in the way how they were being plotted. But Nyquist plot has both of the information contained in the same plot, and only frequency response is needed, and we don't need to explicitly solve the differential equation. That is the whole logic of doing frequency domain stability analysis, so that we don't have to deal with the systems in time domain, right? We move everything to frequency domain. Frequency, by frequency domain I mean omega domain, which is related to S domain. So we do our analysis in S domain, and then we don't solve the differential equations. It's just based on how the in what is the way in which we or how far we are from destabilizing the system. So in the next class we'll see what margin do we have before we are going to destabilize the system. Or if you talk about the Bode plot, then in that case also we talk about margins, and we'll see that. But if we talk about root locus, so for root locus it is like how the poles are evolving as the system parameter is varied. But in all these cases, without solving any differential equation, uh, we are, and without writing the characteristic equation, we are able to find how the closed loop poles are going to evolve. So, and what is the point after which we are going to reach the verge of instability, right? So that is the whole point of doing this frequency domain analysis, right? Okay, so let's see what was covered. So it's basically the plot of Gj omega of the Planck transfer function in the complex plane. On the real axis you have uh, real part of the transfer function, and on the y-axis you have the imaginary part of the transfer function, and we vary omega from 0 to infinity, right? So in this case, let's say if your transfer function is gs is equal to 1 upon s, then gj omega is 1 upon j omega, right? So it is going to be minus j upon omega, and if you split it, it is going to be uh, with a magnitude of 1 upon omega, and the phase is going to be minus 90 degree, because we have minus j coming in. If it would have just been j, it would have been 90 degree, right? But since we have minus j, so it is minus 90 degree. Now for gs is equal to s, it's j omega, so it's going to be 0 plus j omega, which is omega at an angle of 90 degree. right? So these two are very simple. We don't have any problem over here. What problem starts from here? 1 upon ts plus 1. Now how do we draw the Nyquist plot for this? So you just have to take very simple steps. It is something that you won't forget. You just have to find out these points at uh, the at omega is equal to 0, at omega is equal to infinity, and at omega is equal to corner frequency. That's it. You have to find out the real part of the transfer function, imaginary part of the transfer function, magnitude of the transfer function, and angle of the transfer function at omega is equal to 0, omega equal to 1 by t, and omega equal to infinity. That is all. If you have this much information, you can construct the complete Nyquist plot just based on this information. That's it. All right. So what do we do? So let's see for this example. So if for gs is equal to ts plus 1, so if you convert it into j omega form, it's going to be 1 upon 1 plus j t omega, right? Now what is the real part and imaginary part of it? So what we'll do, we will multiply with 1 minus j omega in the numerator, in the denominator, and in the numerator as well, so that we can get rid of any complex terms in the denominator and and have only complex terms in the numerator. So we can clearly say that this is the real part of the transfer function and this is the imaginary part of the transfer function. That's the whole goal, right? So you multiply this with 1 minus j omega, and then you get 1 minus j omega in the numerator, which can be split in two forms, so that we have a real part and we have an imaginary part. Right. So once you have these parts, and if you try to find out the magnitude of this whole transfer function from here itself, you can write 1 upon t square omega square plus 1. That is what is written here, and phase it is minus tan inverse omega t, right? So that's really simple. Now what you have to do here is, once you have all of these values calculated, right, you have the real part, you have the imaginary part, you have the magnitude, and you have the angle. Just substitute 0, 1 by t, and infinity. That's the whole business. So when you substitute 0 in the real part, what do you get? It would be 1. If you substitute it in the imaginary part, it would be 0. If you substitute it in the magnitude, it's going to be 1 upon, it's going to be again 1, and for angle it is going to be 0 degree. Similarly, substitute 1 by t and infinity. So this is what you are going to get. Okay. Now based on this itself, we are going to draw the Nyquist plot. And to be very honest, many of the times when you draw the Nyquist plot, you might get a circle. And so this is a simple thing that I am telling you. When you get in the exam a Nyquist plot, look if it is a circle. Look for this. It could be a circle, and it would be easier for you to debug that. Okay. So and how do we do it? So when you plot all of these, so let's say the real part is 1, the imaginary part is 0. So it is basically this point, right? This point. The magnitude is 1, so it is going to be 1 at a distance of 1 on the real axis, and the angle is 0 degree. So definitely any point on here would have an angle of 0 degree, and there is no approaching even, like it is going to start only from there, so it is at 0 degree, not a problem. If we move to 1 upon t wala case, it's 1 by 2 and minus 1 by 2. Okay, so x is 1 by 2 and y is minus 1 by 2, so it's going to lie here. You should, okay, even now we don't have any sense, we just know that we have got 2 points. One point is here, one point is here. I don't know where the third point lies. Look for omega is equal to infinity, you'll get it at 0, 0. Now once you have this, you should be suspecting it to be a circle. It's very natural, because the middle point that you have got has the x coordinate on the real axis, that too in the middle of 0 and omega, right? And the other thing is, the other point that you've got in y is also at the same distance, half, from the center that you have found. So it's going to be a circle. Now the proof can be done from here, that once you, like, you can always prove it, but my whole point is, whenever you get a system, look if it is a circle by considering these 3 points. Okay. Similarly, the other example that was covered was for 1 upon ts plus 1. So in a very similar way, you have to segregate the real part of the transfer function and imaginary part of the transfer function. And then you have to find out what is the magnitude and what is the phase, right? And you just have to check at omega is equal to 0, 1 by 2 and infinity. When you check, you will see it's at 1, 1, 1, 0, 1, infinity, 1 to infinity, 0, 45, 90 degree. So what happens in this case? The real part is at 1 comma 0 for omega is equal to 0, which is here. For 1 by t, it is at 1 comma 1, which is here. And for infinity, it is 1 comma infinity. That means it is going to go along this axis, because infinity we cannot show, and y-axis is infinity, right? Now you look for magnitude. Magnitude is 1 root 2, so 1 is here, root 2 is here, which is coming at this, and infinity is infinity. Angles 0, this is at 45 degree, and this is at like 90 degree, because it's going to be parallel to the imaginary axis. So this is 90 degree. I hope it is clear. Okay. If it is clear, then let's move to this example. So what is happening here? GS is given by s plus 1 upon s plus 10. Then we are supposed to construct the Nyquist plot for it. So if you just write it, it would be 1 upon 1 plus j omega and 10 plus j omega. We want to get rid of any complex term in the denominator, so we are going to multiply with its conjugate, so that we only have the real and imaginary part to decide from the numerator, and you get this to be the real part and this to be the imaginary part, right? And then you find out the magnitude. This is your whole magnitude, and then the phase is this. Now in this case there are two corner frequencies, right? One for 0, one for pole. We could have 1 upon t1 over here and 1 upon t2 over here, but that is to get more clarity on the system. So what happens if you so here your omega is 0 and infinity, that was taken. It was because when you have an experience, you can just deal with these 2 points and get an answer. But to get more confirmation on your answer, you should have 1 upon t1 and 1 upon t2 also coming into the picture. Now, since we have just 2 points, it's going to be for omega is equal to 0, 0.1 comma 0. So this is the point. For omega equal to infinity, 1 comma 0 is the point, so this is the point. And then this equation satisfies, which is circle with a particular radius. Okay, not from here, it starts from here. Alright. And so this is something that you need to derive. You definitely need to find out what is the center point and if this equation is being satisfied. Alright. Now there are some questions, there will be similar question in the example also that will be covering. So we want to find out when is the maximum phase of this g of j omega. The maximum phase is that if it is a circle, The maximum phase or the maximum angle that you'll get is when it is a tangent to the circle. So for tangent to the circle, we just need to do the calculation so that we are able to find out what is the maximum phase, and the frequency that stays corresponding to that maximum phase is called the corresponding frequency. Alright, so this is everything that was covered in Nyquist plot. After this, we'll have Nyquist stability criteria that we are going to see in the next class definitely. But now we have many questions coming in. So from here, okay. So the plot of the real part of the sinusoidal function and its imaginary part as frequency is varied is called what? It's called Nyquist plot. Okay. Now let's start from here. Which one of the following statements is true about Nyquist plot of the factor 1 upon s plus 5 as the frequency is varied? Basically, we need to find out where would it lie, in the first quadrant, second quadrant, third quadrant, or fourth quadrant. That is the whole question, right? So let's start. So our transfer function is 1 upon s plus 5, and here s is j omega, and omega is being varied from 0 to infinity. Okay, so what we have to do here, we have to substitute j omega. G of j omega is equal to 1 upon j omega plus 5. We want to get rid of any j in the denominator, so it's going to be okay. So from here it's going to be 5 minus j omega upon 25 plus omega square, right? From here we can separate it into real and imaginary part. So g j omega is equal to 5 upon 25 plus omega square minus j omega upon 25 plus omega square, right? It is separated, and once it is separated, we need to analyze the real and the imaginary part. Like if you analyze them, you'll be able to see in which quadrant it is going to lie. So we know that our omega is going to vary from 0 to infinity. So our real part of g j omega is 5 upon 25 plus omega square. So as omega is going to vary from 0 to infinity, this is always going to remain greater than 0, right? So it from here it is definite that it is going to have the real value to be 0. So it's going to lie either in the first quadrant or in the fourth quadrant, right? This is first, second, third, fourth. So it's going to lie either in the first or fourth quadrant. Now let's look at the imaginary part. It's minus j omega upon 25 plus omega square. This is always positive. This is omega is always positive, so the minus sign tells that it is always going to be negative. So it's going to lie where, in the fourth quadrant. So it would lie in the fourth quadrant. So D is your answer. Okay, I hope there is no confusion here. Okay, if there is no confusion, let's move to the next question. Okay, as frequency is varied from 0 to infinity, the Nyquist plot of 1 upon s plus 5 is a semicircle whose radius is what. Okay, let's check it out. So the transfer function is 1 upon s plus 5, right? It can be written as 1 upon j omega plus 5. So if you in the same way, if we take the conjugate and multiply, it would be 25 plus omega square. Okay, now let's find out what is the real part and what is the imaginary part, as omega is 0 and omega is infinity. We can go for another 1 by t as well, but I'm skipping it for now, and I'm checking at omega is equal to 0 and infinity, because we have already known that it is going to be a circle. Anyway, if we are able to have 2 points, then we are going to find the point midway as well, right? It's going to lie on the same line. So the real part, uh, for omega is equal to 0 is what? 5 upon 25, right? Which is 1 upon 5. And imaginary part is going to be 0. Just a second. Okay. So for omega is equal to infinity, what would be the case? The case would be, since it's going to be 5 upon 25 plus omega square, and when you substitute the value of omega to be infinity, it's going to be 0. And for imaginary as well, it is going to be 0. So when you plot it, obviously definitely you should find the magnitude and the angle that you have to do, and from there you will see that you will get 0 degree and 90 degree for angle. That is important. Minus 90 degree. Okay, so when you plot, what would happen, let's see. So this is 0 comma 0 and this is 1.5 comma 0. The circle is going to lie between this is at omega is equal to 0. This is when omega tends to infinity. Okay, so the direction of this Nyquist plot is from here to here. Now, since the question has already said that it is a semicircle, then what is the radius? So what is this midpoint? Midpoint you can just find by averaging the two. It's 1.5 plus 0 upon 2. So this is 1 upon 10, and since it is lying on the real axis, it's going to be 1 by 10 comma 0. Alright, so the radius is 1 upon 10.1. Okay, so A is the answer. I hope there is no confusion over here. Uh, let's move to the next question then. Okay. The Nyquist plot for e to the power minus 5s is a circle of radius what? Again, the question has already mentioned that it is a circle, but how do we know it is a circle? Moreover, the form is also different. So, in this case, gs is equal to e to the power minus 5s, right? When you substitute s is equal to j omega, it's gj omega is e to the power minus 5 j omega. Okay, so this is a pure phase factor, as the magnitude is 1. So if we express it into trigonometric form, what it is going to be? Minus 5j omega is cos 5 omega minus j sine 5 omega. So this is your real part and this is your imaginary part. Okay, now we need to recognize what is the locus of this circle. Okay, so as omega varies from 0 to infinity, we need to check how this vector rotates. How would it rotate? First, since we are already seeing the trigonometric form, we should definitely have in mind that magnitude of g omega is going to be cos square 5 omega plus sine square 5 omega, which is going to be 1. So it lies on a unit circle. Is the equation of a circle with the real part as cos 5 omega, imaginary part as sine 5 omega, and both of them always move in such a way that the distance from the magnitude is a constant. It's a unit vector, right? So it lies on a unit circle. Okay, so it's a circle of radius 1. All right. I hope this is clear. Let's move to the next question. Which one of the following statements is true about the Nyquist plot of the factor 1 upon s square plus 4s plus 8 as the frequency is varied from 0 to infinity? Okay, so in this case, gs is 1 upon s square plus 4s plus 8. Okay, where s is j omega and we want to see when as omega is varied from 0 to infinity, right? So what we'll do, we'll substitute j omega everywhere. So g of j, because we want to separate it into real and imaginary parts so that we can see in which quadrant it is going to lie. So g of j omega is 1 upon j omega square plus 4 j omega plus 8, right? So it's going to be 1 upon 8 minus omega square plus 4 j omega, or we should write it so j 4 omega. Okay, so once we have this, we want to get rid of any j term in the denominator, so we'll write minus j 4 omega, and when we multiply in the denominator, it's going to be 8 minus omega square ka square minus, not minus, plus 4 omega square ka 4 omega ka square, right? So from here, the real part is 8 minus omega square upon 8 minus omega square square 4 omega ka also square. So this real part is omega is being varied from 0 to infinity. Omega belongs to 0 to infinity, right? So if we put the value of omega to be 0, it's going to be 0. But as soon as we put the value of omega to be root 8, the real part is going to be completely 0. Before it were negative, right? It were positive. So for the value of omega to be 0 or 1 or 2 or 3, not 3, up until 2, it is going to be some positive value, right? The real part is going to stay positive because in the uh, denominator we have everything positive since it is a square term, and in the numerator it is going to be positive because the value of omega square would be less than 8. But as soon as we have omega to the value of root 8, then the numerator would become 0. But if we move after root 8, what would happen? For example, value of 5, 6 or something, this is going to be negative. So the real part is going to be positive as well and negative as well, and the changing period is, or the changing point is omega is equal to root 8. Okay, so it's going to be in two quadrants, the real part is going to be positive as well as negative, so it is going to lie definitely in both first and second quadrant. But we have to get this, uh, it could be in third and fourth quadrant as well, so it depends now how the imaginary part behaves. So the imaginary part is minus 4 omega upon 8 minus omega square cos square plus 4 omega cos square. So as omega varies from 0 to infinity, this whole term is going to be negative forever, because the denominator is always positive and in the numerator will have the term to be negative. So since this term is negative, that means we are going to stay in this and this quadrant, right? So it would always lie in third and fourth quadrant. Everything is clear? Any doubts here? Okay. So let's move to the next question. As frequency is varied from 0 to infinity, the Nyquist plot of this transfer function is a semicircle whose radius is what? Okay. So let's do this. Since it has already said it is a semicircle, we are going to just find out the middle point. Okay. So what we'll do? GS is equal to S plus 2 upon S plus 5. Okay. Replace it with j omega. It's going to be j omega plus 2 upon j omega plus 5. Get rid of j in the denominator, so we'll multiply it with j omega, sorry, 5 minus j omega, and here also 5 minus j omega. So what would be in the numerator? It would be 10 plus omega square plus it would be 3j omega, right? 5 omega j omega minus 2j omega. It's going to be 3j omega upon omega square plus 25, right? So if we real and imaginary part at omega is equal to 0 and at omega equal to infinity, so if you put the value of omega to be 0, what would happen in the real part? It would be 10 upon 25, right? 10 upon 25 is 2 upon 5, so it is 0.4, and for imaginary part it is going to be 0. For omega tends to infinity, for omega tends to infinity, we'll have to check. So see, limit omega tends to infinity, 10 plus omega square upon 25 plus omega square. So what we'll do, we'll divide both numerator and denominator by omega square. It would be 10 upon omega square plus 1 upon 25 upon omega square plus 1. It would eventually remain to be 1. So 1 is here, and then after this imaginary part would be 3j infinity. Infinity would come in the numerator, right? Okay, we are going to do the same thing here as well. Limit omega tends to infinity के लिए 3 omega upon omega square plus 25. So from here if you put, we cannot solve it directly, right? We cannot put the value of infinity over infinity. So there is a rule for 0 by 0 form and infinity by infinity form, right? In that case we have to always divide. So here we'll write limit omega tends to infinity, divide by omega square. So it would be 3 upon omega upon 1 plus 25 by omega square. So if you see, in the numerator we'll have 0 and in the denominator we'll have 1 plus 0. So it's going to be 0. So your imaginary part is 0. Okay. So with this we have been said that it is a semicircle and what is the radius. So let's plot it. So it's going to be at omega is equal to 0, it's going to be zero point 0.4 comma 0, and as omega tends to infinity it's going to be 1 comma 0. So these 2 points, if you try to find out what is the difference, it's 0.6. So at 0.3 you'll have, so 0.4 plus 0.3 is 0.7 comma 0, right? So the radius is going to be, the difference between 0.4 and 1 is 0.6, and 0.6 by 2, so 0.3 is the radius of the circle. All right. Okay, I think it is clear. In the same problem, the frequency at which the phase of the sinusoidal function is maximum is what? Let's draw it once again. So we had 0 0.4 comma 0 for omega is equal to 0. Omega tends, it was 1 comma 0 for omega tends to infinity, and then there was the circle with the center at 0.7 comma 0, right? We want to know the frequency. What is the frequency at which the phase of the sinusoidal transfer function is maximum? When would the phase be maximum? When the line originating from the origin would be the tangent to the circle. Sorry, I drew a chord. And it is a okay, when it is a tangent to the circle. Okay, so tangent, not able to draw tangent properly. Okay, let's assume this is the point of intersection with tangent. Okay, so what is this? This is zero point 0.3, because 0.3 is the radius. Okay, what is this? This is 0.7. This whole thing is 0.7. This distance is 0.3, and then 0.3, and this is 90 degree, right? The angle made in between the radius and radius from the center of the circle and the tangent is 90 degree always. So this is 90 degree. Why we are calling this to be maximum phase? Because this is the maximum. So if you have a line here, it is not the maximum phase, it is intersecting the circle, right? But it is not the maximum phase of the circle, because this angle is not maximum. Okay, if we have another line here, if we have another line here, all of them are not the maximum. What is the maximum? When it becomes a tangent to the circle. Okay, so here it is a tangent, so let this angle be phi m. Okay, so sine of phi m is zero point 0.3 perpendicular upon hypotenuse, 0.3 upon 0.7. Okay, from here we want to find out what is tan phi m. So you can always find out, right? It's perpendicular upon base. So you can find this out. Once you have this, it will come out to be 0.474. All right. And what is the phase for our transfer function? It is 3 omega upon omega square plus 25. Right? Or there is something wrong over here? I think no, this is not the phase. I did it wrong. The phase is the term associated with j upon the term associated with the real part. I mean, it's going to be omega upon, sorry, 3 omega upon omega square plus 25 upon 10 plus omega square upon omega square plus 25, right? This is the phase, the real part, this is the real part, and this is the imaginary part. So from here it comes out to be 3 omega upon 10 plus omega square. So if you equate it to be to 0.474, from here you will get omega to be approximately equal to 9.16 radian per second. So, sorry, not 9, 3.16 radian per second. So this is the answer. Any confusion in this question, or was it clear? The maximum phase part, the maximum phase part is when it becomes tangent to the circle, and for that phase you have to find out what is the angle for finding out the angle. I'm sorry, you have to find the angle which you get from tan phi m, and that tan phi can be associated with the angle obtained from the transfer function. When you equate the values of omega, you get at what frequency this is happening, and this frequency is called the corresponding frequency. Okay. Is it clear, or if there are any questions, I can clarify this again? There is no question? Okay. Okay. As the frequency is varied from 0 to infinity, the Nyquist plot for this transfer function would lie in which quadrant? Okay. So at GS, it is very similar to two questions that we did earlier. Okay. You substitute j omega, S is equal to j omega. What you'll get? You'll get j omega is equal to j omega plus 2 upon j omega plus 5, right? Multiply the numerator and denominator because we want to get rid of any j term in the denominator. So j omega is equal to 2 plus j omega into it's going to be 5 minus j omega, and here it's going to be 5 plus j omega into 5 minus j omega. So from here it's going to be 10 plus omega square plus j into 3 omega, right? And here it's going to be 25 plus omega square. If you separate the real and imaginary part, so the real part is going to be 10 plus omega square upon 25 plus omega square, and the imaginary part is going to be 3 omega upon 25 plus omega square. All right. So as omega is varied from 0 to infinity, this would always remain to be positive because everything is square square square, omega is squared. In this case, as omega is varied from 0 to infinity, the numerator is the denominator is anyway going to stay positive for the numerator, since the omega is going to be positive in between 0 and infinity, so this would also always be positive, right? So if the real part is positive and the imaginary part is positive, the quadrant is going to be first quadrant, right? So we have 15A. Okay, I think we are done with today's lecture. If you have any questions, please let me know. And before you leave, in the next week, in the next week there is an update. So we are going to have two sessions in the next week. It's on Monday and on Tuesday, both of the days. On Monday it is going to be at the same time 6 to 8, Tuesday as well at the same time 6 to 8. So we basically have three sessions remaining. right? So one of them is on Monday, one of them is on Tuesday, and the other one is on next Monday. So Monday is usual, it's going to be usual only. For Tuesday we are going to have one another session. Now the thing is, in the next Monday's class we'll be covering the next week's syllabus, which would be Nyquist stability criterion as well as relative stability. And in the on Tuesday, the next Tuesday, we are going to have questions on compensators. So lead and lag compensators. So basically the two last week of lectures would be covered on next Monday and next Tuesday. And then on the last Monday, just a second, let me finish this. And on the last Sunday, sorry, Sunday I'm saying, on the last class, which is going to be, so what is the date today? It's 29. Then on 6th and 7th we have the session, which is coming Monday and coming Tuesday. And then we have the next session on 13th. Yeah, 13th would be the last session, and we'll have a number of mathematical problems that we are going to cover over there. MATLAB problems, I'm sorry. We are going to cover a number of MATLAB problems there. So please try to complete 2 weeks course, the 2 week lectures that have been taught by Professor Shankaram, and come up prepared next week on Monday and Tuesday. It would be helpful for you as well. So cover Nyquist stability criterion, relative stability, and compensators, so that we can have a very fruitful session on Monday and Tuesday, and you can ask all your doubts that you faced while you viewed the lecture or while you completed your assignment. And in the last class we are going to have MATLAB questions related to everything that we have seen right from the first lecture to the last lecture, because we haven't had any MATLAB session in between, which I thought I would do like previous year. So if you go to my YouTube channel, I have previous year's recording also. There also we have a number of MATLAB questions, but that were covered with the class, the regular class. But this time I did not cover it in on a regular basis, and I'm going to cover in the last lecture for everything. So there will be a couple of questions which will be solving using MATLAB. I request you to have MATLAB installed with you. If you do not have the license and your college does not provide you the license, so in that case you can use Octave. Octave is a open source software that you can use instead of MATLAB. Syntax and everything are mostly similar. We are not going to do Simulink. It is going to be a just programming. All right, and yeah, in the next class we have a few questions on Nyquist stability criterion. Nyquist stability criterion would be basically the extension of what the plots you're drawing. It is just that we are going to have some conditions because of which we are going to define some stability of the system, that if we are going to encircle -1, 0, the number of times we are encircling, that defines what is the if the system is stable or not. And after that we are going to have compensators. Compensators are very similar to PI and PD, lag and lead compensator and lag lead compensator. All of these will see, and we'll also see why all of them are important. Why do we want to attenuate noise, or why do we want to increase the gain? All of those things will be seen there. All right, okay, I'm done for today. I think Vignesh asked me some question. If anyone want so I'm done with the lecture. If anyone wants to stay, you can stay, else you can leave as well. Thank you for the session. Thank you for attending the session. uh, I'm aerospace undergraduate student. Will you recommend any course for aerospace? I haven't studied aerospace actually, so I won't be able to guide you properly on this, but uh, wait. So I see there is a lecture by Professor Rajkumar S. Pant from IIT Bombay on the lecture on Introduction to Aerospace Engineering. I don't know what exactly you want to study in aerospace. I'm not sure about this. So apart from that, I'm not an expert there. I know electrical engineering. I haven't taken any specific course for aerospace, so I won't be the right person to guide you on this. But the way I would approach your problem is aerospace controls. So yeah, I can repeat it. Just give me some time, Shubham. I'll come back to the last question. For aerospace controls, so do you know control systems completely? I mean, I think the control system that we are going to use there is based on the similar analysis that we do now. So what I would suggest you, complete this course first, the control system, because this is the basic founding block of any system that you are going to control. So after you complete this course, you can have the course on modern control system. That would be helpful for you. uh, I'll tell you the exact lecture which you can watch for modern control system. And then for aerospace, exactly what control system is used, I'm not sure about that. What you can do is, you can look for any lecture if it is available on NPTEL. It is going to be just a search. If it is not there, so I saw that introduction to aerospace engineering is there, but aerospace controls seems to be more on the control side. And if it is not there, go for Coursera or edX. Try to find out the lectures there. You might get a good lecture there from any US university or any foreign university. Try to start watching that lecture, and if you are able to grasp what is being taught there, continue with the course, submit the assignments, and you'll be able to learn. See, I'm not in aerospace, so I won't be able to guide you properly on this, but this is how you can approach this problem. So uh, do it in this way. Look for the lectures on NPTEL, move to Coursera or this edX. So from there, I think it will solve your problem. Okay, I hope I have been able to answer to the best of my knowledge. I'm sorry, I'm not an expert in the field, and I won't be able to like tell you any further. Okay, Shubham. So uh, this question is very similar to what we covered before this. So in this, what we are going to do, as frequency is varied from 0 to infinity, where would the Nyquist plot lie? So it's just going to be, you have to convert it into j omega form and get rid of any j in the denominator, so that you get a transfer function of this form, right, where you have a real part in the numerator and the imaginary part in the numerator. Like, denominator should be free from any complex terms. So from here, what is the real part? It is 10 upon omega square upon 25 upon omega square. And what is the imaginary part? 3 omega upon 25 plus omega square, right? Now, omega is being varied from 0 to infinity. That is known, because that is what we check for Nyquist plot, right? So omega is being varied from 0 to infinity. So from here, if you see in the real part, it's 10 plus omega square. Since omega is being varied from 0 to infinity, so numerator is positive, the denominator is also positive, so real part is always positive. For imaginary part, denominator is a square term and it is going to stay positive forever. For the numerator, it's 3 omega, right? And omega is being varied from 0 to infinity. That means it is also going to stay positive. So again, it is in the it is going to have the value greater than 0, and hence if both of them are greater than 0, it's going to be first quadrant. Okay, I hope it is clear. Okay, see you next Monday at the same time. Thanks.